Okay, so good, whatever time it is where you are, everyone. I'm Mattia Welsgaard. I'm a CNRS researcher at the Laboratoire Kastler Brossel in Paris, and I'm going to talk about multimode non-Gaussian states, and I'm going to give you the theory perspective of that. So to dive right in, I will talk about continuous variable systems. So in optics, the continuous variables are going to be the quadratures of the electromagnetic field. But you can basically think of this a bit as a bunch, like as your electromagnetic field, which has many modes, as being kind of an ensemble of many quantum harmonic oscillators. And the field quadratures are basically going to be like the position and momentum of these quantum harmonic oscillators. So why do we like this continuous variable approach in quantum optics? Well, it's because this allows us to make very large entangled states. So here you see one example from the group of Akira Furuzawa, where they made these very large cluster states where every little vertex represents a time mode, so a kind of a time bin. And with techniques from temporal multiplexing, you can basically get these very large entangled states. So every link here represents some entanglement. And of course, various other groups have also created these big entangled states, so in slightly different ways. But the idea is that we can get a lot of entanglement. The downside is that when we look at these states, that they are actually Gaussian states, which means that when we are actually going to measure these field quadratures, that we are always going to get Gaussian measurement outcomes. And this is something that is easily simulatable on a classical computer. So if we want to go beyond and we want to get really do quantum information protocols that cannot be simulated on a normal computer, so which really have a quantum advantage, what we need is Wigner negativity. So here I show you the Wigner function for a single mode, and you clearly see the negativity here by this little bump that appears. And so this is known to be a necessary ingredient to get a quantum advantage. And so what we try to do in our group is to combine these both aspects to make these reasonably large entangled states and induce this Wigner negativity in them. So how do people generally create Wigner negativity? Well, you first of all have a whole set of deterministic methods. So you could, for example, think of single photon sources based on quantum dots, where you basically push a button and a photon flies out. A photon has a negative Wigner function, so technically you have created Wigner negativity on demand in a deterministic way. However, in optics, what is more common is to use probabilistic methods. Like, for example, in this reasonably old paper, you see that they produce also single photon Fock states by generating first a very weakly squeezed two-mode vacuum, so that you get basically a lot of vacuum, and every now and then a pair of photons which is created. So one photon going in this direction, the other one going in the other arm. And when we detect a photon in one arm, we know that there is also a photon present in the other arm. And so this is then a way of creating single photon Fock states. And of course, it's probabilistic because it depends on whether or not we detect a photon in one of the two arms. So we can extend this kind of idea to make more exotic states. So here, for example, what they have done is they create a single mode squeezed vacuum. They send it through a very highly transmitting beam splitter. So almost all of the light is transmitted, and just a very weak fraction is taken out and sent to a photon detector. And if you get a click, you know that actually exactly at this moment, there is one photon missing in this beam here. And so we heralded a photon subtracted state, which still has some of the squeezed properties of this initial squeezed vacuum state, but now has inherited this kind of non-Gaussian feature, this Wigner negativity of the photon subtraction. And so what we do in our group is we do this for not just one mode. So this would be like one quantum harmonic oscillator, but we do this for many mode light, so in highly multimode light, where you actually can think of having many quantum harmonic oscillators. And what we want to do is we want to be able to control precisely in which mode, so in which harmonic oscillator or in which superposition of harmonic oscillators we are going to take out the photon. And so I'm not going to to immediately talk about this specific setup, but what I want to do first is to kind of in general present these probabilistic methods in a more kind of structured theoretical framework. So this is the more detailed outline of my talk. I will first present a general phase-space formalism to describe these conditional operations and these conditionally generated states. Then I will show you how we can apply this formalism to model photon-subtracted states. And then finally, I will do some part which is more a hybrid between theory and experiment, explaining how we can then, with which measurements we can use to characterize these non-Gaussian states and how this works. And then at the end, I will end with a little outlook and a little take-home message as well. So first things first, so we are going to look at conditional state preparation. And so to me, as a theoretician, every kind of quantum optics experiment that does conditional state preparation looks more or less the same. You have a source that's going to produce multimode light. And I don't care whether it's spatial modes, time frequency modes, whatever. The only thing which is important for me is I can make a bipartition in my system. I can split my system into two groups of modes, where one group is called G and the other group is called F. Now, I'm going to suppose that my source produces states that are easily produced in experiments. So typically these will be Gaussian states. So what this means then is that I'm also going to assume that there is some kind of a correlation between the modes in F and the modes in G. This does not necessarily have to be a quantum correlation a priori, but you need some correlation for something to happen. Because the next thing that we want to do is we want to do some operation, typically a measurement, on the modes G. And so we're going to condition on a specific measurement outcome, which boils down to, in a theory language, applying one specific POVM element to the modes G. And I want to understand what happens to the state of the modes F. Well, formally, I can write this down in the density matrix formalism, because what will happen is basically I will take the POVM element here that is acting on the modes G. I let it act on the complete state rho, and I trace out the modes in G, because typically I am only interested in the modes F. Then, of course, I have to renormalize this to make it a well-defined quantum state with the success probability of this measurement. So this is basically going to just be the probability that I actually got the measurement outcome on which I'm conditioning. And of course, formally, now we know the quantum state, but this doesn't really tell us anything. So what I want to understand is, in general terms, what are the properties of the Wigner function of this state? More specifically, when does this Wigner function actually become negative? And so to answer this question, I have to translate this whole framework to phase space. So I will associate Wigner functions with everything. So you'll get a Wigner function that describes the global state that is produced by the source, so the initial state. Then I have a Wigner function that describes the operation I'm doing, so the POVM element. If this is a projective measurement, this is going to be the state projected, like the Wigner function of the state on which we are projecting. Of course, this Wigner function is only defined on the phase space associated with the modes G, whereas this global Wigner function is defined on the full phase space. And then the Wigner function that we're actually interested in, this is a conditional Wigner function. This will only be defined on the modes, on the phase space of F. So this conditional state Wigner function can be written down as follows, just translating basically what we had on the previous slide. We replace all the operators with their respective Wigner functions, and the traces are replaced with integrals. So the trace over the modes G becomes an integral over the phase space associated with G. And then the global trace just becomes an integral over all of phase space. And of course, well, then we haven't really made much progress here. We just kind of put in Wigner functions for our observables. But now I can use a very simple trick. I'm going to use the fact that the state that I'm producing here has a positive Wigner function. And this means that it's actually kind of a well-defined probability distribution on phase space, such that I can define, at least in formal terms, a conditional probability distribution on the modes G, by conditioning on one specific phase space variable, phase space point actually in F. And so this conditional probability distribution is just defined by the following identity, where WF is the reduced state of W to the modes F. So if W here, the global Wigner function produced by the source is Gaussian, WF, the reduced state to the modes F, will also be a Gaussian. And I'm going to now use this conditional probability distribution and insert it into this, this expression. And so what I see is that this reduced state Wigner function of F is going to come out. And I have now obtained this integral where I'm integrating this Wigner function of the POVM element now with respect to this conditional probability distribution. So this object, I'm going to call this the conditional expectation value of A. And then at the bottom, I still have the actual expectation value of A. And what we have here, so because A is a POVM element, the expectation value of A is actually a success probability. And this conditional expectation value is somehow also going to be something like a conditional probability, but not completely. It will not have all the right properties. Specifically, it can actually get negative. And so what we have here is something like a Bayes theorem, but for Wigner functions, with all the complications that go with it, like the fact that you can have basically negative values. And so this conditional expectation value is going to be very important, because when we look again at the expression for this conditional Wigner function, we see, well, this is a Gaussian, this is a number. So what is left here, this A, this conditional expectation value, this is actually going to contain all of the non-Gaussianity, the Wigner negativity, and so on of our state. And so I have to kind of insist on the fact that because we condition on a specific value in phase space, so this is the same variable here, so this is going to actually be a function of XF, of the phase space variables in the mode F. And so all the interesting properties are contained in here. So this conditional expectation value is given by this integral. So first of all, this conditional probability distribution is a well-defined probability distribution. So it's always positive, which means that if I want to get Wigner negativity in my state, I need to have Wigner negativity in this POVM element, or in whatever kind of Wigner function I have here on this side. Otherwise, it will not work. But this alone is not enough. So generally, whether I get Wigner negativity or not will also depend a lot on the specific properties of this conditional probability distribution. And in our setup, this is quite interesting, because initially we have a Gaussian state, which means that our conditional probability distribution that we defined is also going to be a Gaussian. More specifically, it's going to be a displaced Gaussian probability distribution, where the displacement will depend on this value XF upon which we are conditioning, but the covariance matrix of this Gaussian does not depend on XF. And it's just given by this Shor complement, where basically this is a Shor complement of the global covariance matrix, so the covariance matrix of the full state, where now VG denotes a covariance matrix that describes only the modes G. Vf describes the covariance matrix that only describes the modes F. Then this VGF is actually the part of the covariance matrix of the global state that contains all of the correlations between the modes F and the modes G. And so this Shor complement is, well, it is what it is, but it turns out to be a very important object also in the theory of quantum steering. More specifically, it turns out that this Shor complement does not necessarily obey Heisenberg's uncertainty relation, which means in return that actually this conditional probability distribution is not necessarily going to be a well-defined Wigner function of a certain quantum state. So when this is the case, so when we have a violation of Heisenberg uncertainty relation in the Shor complement, you can actually show that there will be steering from the modes F to the modes G by Gaussian measurements. So I can do Gaussian measurements on the side F to steer Gaussian measurements on the side G. So what's more interesting is that the opposite is also true. So if I have this steering, I will also have this violation of Heisenberg's uncertainty relation in this Shor complement. And so this is a very important result, because we can turn this around, and it also means that when we have no steering by Gaussian measurements, that actually this covariance matrix will satisfy the Heisenberg uncertainty relation. So this means that this conditional probability distribution is a well-defined quantum state, and this means so that we can associate a well-defined quantum state, a Gaussian state, with this conditional probability distribution, such that basically this conditional expectation value of A will actually be the expectation value of A in this quantum state. And this, because A is a positive semi-definite operator, and this is a well-defined quantum state, this will always be larger than 0. And this is true for every value xf upon which we condition. So as a consequence, when we don't have steering from the modes f to the modes g by Gaussian measurements, we can never get Wigner negativity in this conditional state. And so this is a really fundamental result, because it doesn't depend on the measurement I'm doing. Like I can do, when I don't have the steering, I can do whichever measurement I want on this side. It will never give me Wigner negativity. And on top, it also puts strong constraints on how we can distribute Wigner negativity, because there is a thing called monogamy. So now I'm going to assume that I just have one mode G, and not one, but several modes F. And so there is a concept called Reed monogamy, which is specific for Gaussian quantum steering, for Gaussian states, which says that if I have this mode F1, for example, which can do steering on the mode G, and we have the entire thing defined in a Gaussian state, well, then automatically other modes, F2 and F3, cannot do any steering on G as well. So at most, one of these modes can steer G at the same time. And this has a very important consequence, because we can use it to define a monogamy relation for the created Wigner negativity. So here I'm defining the negativity volume of this conditional probability or this conditional state, just by taking the absolute value of the conditional Wigner function and integrating it. When I have Wigner negativity, this is larger than 1. When I subtract 1, I get exactly the volume of the negative part of the Wigner function. And it turns out that using this Reed monogamy, together with this definition of the negativity volume, that I can show that actually the global negativity volume, so if I do this operation here, the global negativity that I create in this joint set of 3 modes in this case is always going to be larger than or equal to the sum of the local negativities that I get. And due to this steering, there will basically be at most one mode, due to the monogamy, there will be at most one mode that can steer mode G. So at most, one of these negativity volumes will be non-zero. So this is an important point in the proof. And so this means that you have really a very strong relation how the negativity can be distributed. So one important side remark is that it's basically possible that none of these local modes has Wigner negativity, but that the global state still has it. So to kind of wrap this all up, so what we showed is that this steering from the modes F to the modes G is a very crucial and necessary requirement to be able to create Wigner negativity in the modes F by doing a measurement on the modes G. This has important consequences on the level of monogamy and so on. And then there is also an additional result, that is that this is also a sufficient resource, in the sense that once you have this steering, there is always a measurement that you can do here, or an operation that you can do here to get the Wigner negativity on the other side. And this turns out to be photon subtraction. There are probably other ones, but this is at least one framework that we found that always works. You first do a local Gaussian transformation. So you might have to locally change the squeezing and the basis and so on. And then you are going to do a photon subtraction here. And if you have this steering, you will actually automatically get Wigner negativity on the other side. So photon subtraction is clearly something interesting. So let me explain you how we can use now this formalism to model photon subtraction. Well, so let me get back to this picture that I showed before. So this is what we want to do. We have a big multimode state, and we want to subtract a photon wherever we want. And basically, the idea is that we want to take our global state, we want to choose a mode, and so remember that basically superpositions of modes are also modes. If you take harmonic oscillators and you take superpositions of them, you will again get something which behaves as an harmonic oscillator. So we want to be able to choose any kind of superposition of our quantum harmonic oscillators, of our optical modes, define an annihilation operator in it and apply it. This is what we actually want to do. So how do we model this? Well, we do the following. We are going to take our initial state, whatever it may be, defined in a certain mode basis F. And now I'm going to do an interferometer. I'm going to inject a state into an interferometer. And the only thing that I care about is that one of the modes that comes out, which I call B, is the mode in which I want to apply this annihilation operator. This is going to be the mode from which I want to subtract the photon. To then do the photon subtraction, I'm actually going to just assume that I have a beam splitter here. So I'm going to add an auxiliary mode, which initially is in vacuum. And I'm going to couple this to this mode B and take out a little bit of light and then mount the photon detector to do the photon subtraction. So this would, like auxiliary output mode, I will call G. And I will suppose or assume that this little beam splitter is very, very weak. It's going to let pass almost all the lights, except just something that is basically negligible. I'm going to take a limit going to 0 at the end. And then I take a second interferometer here again on these modes F, which is basically going to translate me back to the initial mode basis. So I have the same mode basis here as here, but I have done this additional operation in between. Now, what I want to understand is what is the Wigner function that I obtain here at the output for the modes F? Well, actually, it turns out that this is very similar to what we have discussed before as in this general framework of conditional states, in the sense that these modes F here are going to be the 4 modes that I have here. The mode G here is going to be the little mode G that I have here, and I'm going to apply exactly this framework. I'm going to apply this formula where I have my WA going to be like the Wigner function of a Fock state, because I'm doing a projective measurement on a single photon state. So to basically like make my whole framework work, I need to have the actual Gaussian state of these 4 output modes and the auxiliary mode. And to get this, I take the covariance matrix of the initial state, VF. I add the covariance matrix of the vacuum that I couple in here. And then I'm going to apply this OBS, which basically just contains all of the linear optics and all the interferometers that I did here. It's this matrix, this basis change, it's this beam splitter, and this additional like reverse basis change. And so when I do this whole thing, I have the covariance matrix that I need to apply this whole framework. Okay, so let's put that aside. What we now need is we need to calculate basically just this conditional expectation value. WA is given here by this this Fock state, and this conditional Wigner function, or this conditional probability distribution, I can obtain by taking the Shor complement of this covariance matrix here. And then note, because I'm only having 1 mode in G, I just set this L prime here equal to 1. This counts a number of modes in G. And on top, I'm going to have to take the limit of this beam splitter, where the reflectivity of the beam splitter goes to 0 and the transmittance goes to 1. So when I do all of this, long story short, the Wigner function that I get out is the following, where you see The psi f and the psi b, they are displacements. So psi f is the displacement, the mean field of the initial state. Globally, here I have to take into account also specifically the mean field in this mode B from which I'm subtracting the photon. The VF is a covariance matrix here of the initial Gaussian state. The WF here should be the Wigner function of the reduced state here. But because I take the limits for this beam splitter actually going to 0, it turns out this will just be the same Wigner function as the one that I had here initially. And then finally, I have these objects that pop up, which are here, these B's, which are basically going to be projectors. I'm going to take my full 2m-dimensional matrix, where m is the number of modes that I have in F, and I'm going to project it down on this mode B that I have here. And so this projection, this is done by these matrices B. They take a big matrix and they send it to something 2 by 2. So this is the Wigner function that I obtain. Looks a bit ugly, but we can actually learn a lot of things from it. For example, we can get a quite elegant negativity condition. How do we do this? Well, we have this modulus squared here. It looks quite ugly, but the fact that it's a modulus squared means that it's always larger than 0. It turns out that you can always find a value in phase space xf where it does become 0. So the minimal value that we have here for this part is going to be given by this trace here. And if this trace is negative, well, the whole thing is going to become, the whole Wigner function is going to become negative. So I just translated this, the fact that I want this trace to be negative, to the fact that I want this trace here to be larger than 2. Now, this is quite cute because this is actually related to the Shor complement that I had of this big system sent through the interferometer with the auxiliary mode and so on. Because when I write down this, this Shor complement in the limit where this beam splitter is very weak, the beam splitter that does the photon subtraction, I get the following Shor complement. And basically the case where I have this trace here larger than 2, this kind of quantifies when the Shor complement is no longer going to satisfy the Heisenberg uncertainty relation. So you really clearly get this connection to the steering here that again pops up to see where we have the negativity. On top, and this is also very interesting, this is going to be related to the Fisher information as well of the initial Gaussian state. So basically what I have here is something like the Fisher information that describes measurements when I have this big Gaussian state, and I'm going to do specifically measurements in the mode B. Well, this is going to give me kind of something related to the Fisher information of the state. We don't really understand where this connection comes from and how general it is, but it's quite interesting to highlight that it's there. Of course, what this basically also says is that this condition kind of says that you need squeezing. So you could say you need a metrological quantum advantage, but at the same time, it just says that you need non-classicality in this initial state in the mode that you are subtracting. And so this is maybe not that surprising in this sense. And then again, I have this monogamy relation that applies, which also tells me that I cannot just get Wigner negativity everywhere. When I do photon subtraction, there will be rules that tell me where the Wigner negativity goes, to which modes, and so on. And so in this regard, there is actually a fun fact, because I can apply this conditional formalism in a very different way as well. I can also apply it as follows. I can take G not as the auxiliary mode on which I mount my beam splitter to do the photon subtraction, but I could take G directly to be the mode in which I subtract the photon, and the photon subtraction as a whole as being the conditional operation that I apply. So this means that I'm going to look at the Wigner function now of the other modes. So I'm going to take out the mode in which I'm subtracting the photon, which was B on the previous slide. And I'm going to look only at the other modes and look at the reduced Wigner function for that. And I can capture this with this framework. And now what I have to do is actually, I have to set this observable A now equal to actually the number operator in the mode G. So this is no longer going to be a POVM element, but the whole framework still applies because it's still kind of, you can still see this as related to a general Krauss operator. So everything is fine. And when you then like use the framework again, you basically get this Wigner function, which again has this Schur complement popping up. And now what you see is that you actually get the Wigner negativity when the modes F can now steer the mode G in which you subtract the photon, which has, again, funny consequences. And let me show you this with maybe a simple example. I'm going to take this EPR state, so 2 squeeze vacuum modes, maybe with some noise. I apply a phase shifter here so that they are both squeezed in orthogonal quadratures, and I get this entangled state that comes out. And then I'm going to subtract the photon on one of the 2 arms. So if I want to see whether I have global Wigner negativity, what I'm going to do is I'm going to take the covariance matrix of the full Gaussian state. I'm going to invert it, and then I'm going to project it to the mode B. And if this gives me a value larger than 2, I know that globally I will have Wigner negativity somewhere. At the same time, when I now take this global covariance matrix and calculate the Schur complement for basically this mode that describes how A is steering B, well, if I have that this trace of the Schur complement is smaller than 2, basically this means that A can steer B. And in this case, when I do the photon subtraction here on mode B, actually I will get Wigner negativity in mode A. Now, fun fact, we have the monogamy relation, which means that if I have steering here in this direction, and if I have negativity here, well, monogamy implies that then I cannot have Wigner negativity in mode B. So at the same time, I could basically just forget completely about the existence of mode A, just take the reduced covariance matrix that describes mode B. I can invert it and basically just treat photon subtraction as if I only had mode B. Then I get this condition for Wigner negativity, and then of course the Wigner negativity has to be mode B. And from this monogamy, we kind of get for free, without having to do any calculations, that this condition and this condition cannot jointly be true. And this turns out to be a fact. And so generally speaking, so we can have conditions for global negativity, but we also have a lot of things that happen on the local level. And this monogamy is kind of the tool that dictates what will happen and where negativity can go and where it cannot go. So this is kind of the whole background theory. So now I want to still take some time to tell you actually how we characterize these states in experiments. So I'm going to show you the experiment that we did with the photon subtraction. So here you have the part where we produce the squeezed vacuum, so the initial Gaussian states. Here we have the part where we do the photon subtraction. And then finally, what I'm interested in here is going to be this part. It's the measurement part, because you see we only have one homodyne detector here. However, we have a pulse shaper, which means that we can choose any possible mode, any possible harmonic oscillator or superposition of harmonic oscillators in which we can perform a measurement. So typically the signal that we get out, if we are lucky, will look something like this. So this is actual experimental data. And then we can use these data from the homodyne detector to take an off-the-shelf maximum likelihood algorithm to reconstruct the Wigner function. So this is the Wigner function that we get here. And it has some Wigner negativity. So here I show you that, of course, if we don't have any correlations between the modes, so these HG0, 1, and 2 modes, they're actually uncorrelated modes. You can think of this as uncorrelated harmonic oscillators. And so, of course, when we do this mode selective photon subtraction, and we tune our subtractor to subtract in mode HG0, because it's completely uncorrelated to HG1 and HG2, we expect there to be nothing that happens in modes 1 and 2. And as you see, modes 1 and 2 here, they remain nicely Gaussian. We get Wigner negativity in HG0. There is a little change. This is because experiments are never perfect. Then you see this mode selectivity nicely when we tune now the subtraction to HG1. When you see again that basically when we subtract an HG1 and we measure 0, 1, and 2, that basically again, like the Wigner negativity will go really in one mode and the others are virtually unaffected. Now what's fun is that we can also use the setup to actually get this example that I showed you before in practice. We basically did the measurements before we did all of the theory. So it's kind of fun. We just realized this might be a fun thing to do. And what we saw is, so I calculated these short complements from experimental data. I found that both of them, so in both directions, they give you the same trace, which is smaller than 2. So you expect to see a little bit of Wigner negativity, which is the case. So here I show you, we subtract in EPR0 because there is steering from 1 to 0. I expect actually to see the negativity in EPR1. So if I measure EPR1 and do the reconstruction, indeed I see that there is some Wigner negativity here. On the other hand, when I do the opposite, I subtract in 1 and I look at 2. So this is what is drawn here, and I look at 0. I see that there is a Wigner negativity in 0 and not at 1. Okay, so this is all consistent. Next step. So now this is, I mean, local negativity, you can see it with local measurements. Of course, once you know there is local negativity, you know that there is global negativity as well. However, you might not always be able to see local negativity. So for example, when I give you these data, so this is 10 mode data. These are 10 modes that are measured and for which you get the homodyne traces. When you use your state reconstruction algorithm, you're probably not going to get any local negativity here. I can do the same thing for another state, another trace. Again, you probably will not get any local Wigner negativity in any of these traces. So now my question to you is, well, is there some state here that actually has Wigner negativity? Turns out that the answer is yes. Turns out that it's actually the left one. Why do I know this? Well, not from looking at the data. I don't see much of a pattern here, but I know this because I simulated the data and I know what Wigner function I simulated. And this may sound a little bit silly, but of course you can then wonder, like, well, I mean, it's not because we don't see a pattern in these data that there isn't one. And because we can simulate these data, we did this for thousands of states, and we injected this in a machine learning algorithm. And this works. So we can actually see and predict whether we have Wigner negativity in our state or not based on this kind of data. You see that it works less well for more modes. We have now found ways to improve this a little bit. I prefer still to show you the data that are in the actual paper. Turns out that we were a bit silly. We used the same parameters for different modes, and actually if the algorithm has to be changed a little bit depending on the number of modes, and you can kind of further optimize to also kind of push all the data to, let's say, the 95% accuracy regime. So with quite good certainty, we can check from these data whether we have Wigner negativity or not, especially for small numbers of measurements, even in the regime where you have few modes. This way of doing it is much more effective and much more efficient in the number of measurements than maximum likelihood. And what's really cool is it doesn't even use correlations between the different detectors. So you just can use one detector, measure one mode after the other, inject all these different measurements into this protocol, and it will tell you whether you globally had Wigner negativity or not. So this is very cool. Now I showed you that we can see global Wigner negativity, which is kind of a non-local feature. but it's kind of a global effect. So now the next question would be like, can we really see something on the level of entanglement, quantum correlations, and so on? Well, the answer is yes. You can see you can see correlations. You can see effects in correlations of photon subtraction. And for this, we applied network methods. So here I'm showing you one of these big Gaussian graph states. So every mode represents a squeezed vacuum, and all the connections represent CZ gates, so entanglement gates, to create a big entangled state in the form of some complex network. And then I'm going to subtract photons here in one single mode in the red dot. Actually, we did subtraction of 10 photons for this case. And so what I show you here on the other side, on the right, these are networks that we construct for these states that represent correlations between numbers of photons in different modes. So this is kind of a blueprint for building a state, and this is actually an emergent feature that you then get in this state. So this shows you the thicker the lines are, the more strongly your photon numbers are correlated. If the correlation is 0, well, if you have a 0, there is no correlation. If you have 1, there is an exact correlation between the number of photons between the two modes. And we see that this graph, this correlation network, changes dramatically after. So this is before subtraction, this is after subtraction. And so we see that the features of this network change. Some correlations get enhanced, some correlations are created. And what we see is when we look at every individual vertex, we look at the sum of all the correlations, the correlation links to the other modes, we really see that there is this gigantic correlation that is created. We see that the degree, as we call this in network theory, is really changed. And then we try to figure out how this happens. So we found out that there is a big effect of distance, where I talk about distance in this imprinted network of CZ gates. So the vertices that are really the strongest affected, so the correlations that are boosted the most, they are at the vertices around the node where you subtract the photon. Then you have the ones that are one step further removed that are still affected quite strongly, but the ones that are further away, they more or less give you the same distribution as you would get for the Gaussian case. So then we found that there is this kind of funny structure that appears in distance 1. Like you have a lot of the correlations that are boosted, but some of them are not boosted at all. And we found out that this actually depends on the structure that you have here in the subgraph of distance 1 vertices. So it depends on how these different modes are connected among each other. So basically the idea is if many of your nearest neighbors are connected to each other, you will get a lot of increase in correlation. Whereas if basically you have kind of lonely individuals, if you just have like one of your nearest neighbor that is not connected to any other nearest neighbors, actually the correlation will even be reduced a little bit. And so this shows us that these network methods, they can really teach us a lot about the correlations that we have in these systems. And so now I want to first of all give you a little take-home message. So what I showed you is that we have a general model to describe conditional operations on phase space that really emphasizes the importance of Gaussian steering and in relation to Wigner negativity. We also have used in this model to describe multimode photon subtraction, which even can be extended to subtraction of multiple photons. I have not really showed this. It's much more complicated on the level of calculations and formulas. But so in principle, it can be done. Funnily, a lot of the work that we did on Wigner functions of photon subtraction, we did actually using other methods. It's only later that we developed this general method that actually was very appropriate to rederive all of these results. And then finally, I also highlighted that network methods and machine learning methods are really useful for understanding what is happening, let's say more on an experimental level, understanding what is happening in these non-Gaussian states and what the effect of these non-Gaussian operations is. So then finally, I want to kind of give you bit of an outlook. So the first thing that we want to do is we want to now more deeply study what happens to entanglement and steering in these non-Gaussian states that we create. So develop a theory of non-Gaussian entanglement, non-Gaussian steering. So we have a first result on this that's on the archive at the moment on non-Gaussian entanglement. Then we want to really focus more on these network methods in particular, and understand not what we can say about correlations, but what we can say about quantum correlations in the states by using these network methods. So this is another big open question that we have at the moment. And then finally, more on the long term, we want to understand how these non-Gaussian effects that we create could be used in quantum information protocols, maybe to get some quantum advantage, but also in quantum, like in enhanced sensing, in quantum metrology, and so on. So I want to give a quick shout out to my collaborators. So for the steering and particularly the parts on monogamy, we work together with the group of Chongyi He. So here you see Chongyi. You also see Yu, who did a lot of the work. She was kind of the postdoc who was in charge of all of this. Then there is also Xu Hang in particular, who did also a lot of the work. I don't have a picture of him, but so he also did contributed a lot to this work. And then on the other side, there is for the machine learning, we had a nice collaboration with the people from Rome, specifically the group of Marco Barbieri and especially Valeria Cimini, who came to our group for a few months just before the COVID fun happened. So she was lucky to still be able to travel, and we were lucky to still be able to get some nice results at the end of 2019. And so really this worked remarkably well and quickly. And then there is our group. So I really want to thank the people in the Multimode quantum optics group at LKB. So the other permanent people in the group are Nicolas Treps and Valentina Parigi. So you see, this is a picture taken quite recently. Some of the people, many are experimentalists. So except for Giacomo, who is not on the picture, and Ilya here, who just arrived, all the other ones are experimentalists. So they regularly go to the lab, which makes it we can still, when we all go outside and keep masks on and so on, we can take some pictures. So this is more or less part of the group at the moment. And then as a last permanent member, we also have Claude Fabre, who is traveling a lot, who is an emeritus now. So he's basically enjoying science and life. And then I want to close with a propaganda slide, which basically contains all of the references of the work that I talked about. And in particular, I want to highlight this tutorial that I recently wrote on basically non-Gaussian quantum states in multimode continuous variable systems, and more or less all I know about them. So it's really supposed to be a rather pedagogical introduction in methods, important results, and so on. And so if you want to really learn things about the technical details, have a look, drop me an email if you have questions or if you find mistakes. And yeah, I hope this can help some people who want to get into this this line of research. And I thank you very much for your attention, and I welcome all the questions. So since I might put this video on YouTube, well, if you have questions, feel free to ask them in the comments section. And so just as a little context, so this is a talk that I'm going to give tomorrow morning well, it will be evening in Singapore when I give the talk, but so it's I got invited for a seminar at the Center for Quantum Technologies in Singapore. So this is where this talk will be given, or some incarnation of this talk will be given. So, well, thank you for listening and for sticking by me throughout the whole talk, and I hope you enjoyed it. Bye-bye. Now I just have to find out how to stop the recording.